So after we have been able to learn the concepts of exponential functions, maybe we could have some of these examples. These examples are actually part of the basic concepts, plus some additional examples on the different applications, basically the models that would govern exponential function. So here, how do we determine if given functions are exponential or not? So the first example is f of x is equal to 5 to the power of x. Now, we know the fact that our 5 here is the base of our function. So that is b. And the value of a here is 1. So in that case, we take into consideration our given f of x that is equal to a times b to the power of x. Then this is equal to 1 and this is equal to 5 raised to the power of x. And so this is equal to 5 to the power of x. That means this is an exponential function. Let us move on to our second example. We have 3 times x to the negative third power. This is not an exponential function. That is because you see here that our x is not used as an exponent, but instead it is used as a base. Therefore, this is not an exponential function. For the third example, negative 4 quantity 2/3 to the power of x. This is an exponential function because we see that your negative 4 here and 2/3 are used as our initial value and as the base. For the fourth example, m of x is equal to 9 quantity negative 2 raised to the power of x. This is not an exponential function since the base is not a positive number. Take note that our base must always be greater than 0. Therefore, this is not an exponential function. Now, let's move on to the evaluation of given functions. So how do we evaluate functions? We have the first example is p of 5, given that the function is p of x is equal to 2 times quantity 2/3 to the power of x. Okay? So in that case, we have the first example. P of 5 is equal to 2 times the quantity 2/3 to the 5th power. So we all know that this is actually equal to 2 times, what is 2 to the 5th power? 32. And 2 to the 5th power is 243. Making this 64 over 243. Okay. Now let's have letter B. If x is 0, automatically it follows that the rule for 0 exponent, 2/3 to the 0 power is equal to 1. Therefore, what happens is that your 2/3 to the 0 power is just simply equal to 1 multiplied by 2 is equal to 2. Okay, let's move on to our third. Okay, x is equal to pi. So if x is equal to pi, then maybe we could make use of our calculator to find for that value. How do we do it? Okay, so we just simply multiply 2. Then we have our fraction is 2/3. Okay, so it's 2/3 close, and then our exponent is pi. And then that's basically your shift scientific notation key. So pi is already there. That's equal to approximately equal to 0.5595. So that's it. Okay. So moving on, we have our letter D example. We have x is equal to 1/2. The value of the function would be equal to, what's that, 1/2. So maybe we could solve this manually. Raised to the power of 1/2. And we all know that when we take the square root of any given quantity, we're actually raising it to 1/2. So this means that this 2 will be equal to the square root of 2 over 3. So, okay, that's just about it. Here's our answer. Now, we try to solve problems that would relate with this kind of situation. Suppose a rumor originally known by 100 people, and the number of those who would know in the future doubles every day. So there's a certain rumor initially known by 100 people, and we will try to determine the number of days that rumor will be known by 350,000 people already. So in this case, there's a need for us to form first the equation. So maybe it would just be proper for us to represent first the rumor with tables. So the table is like this. On the left column, we have here our t, and the right column is r of t. And then we know that the initial value here, the initial number of people that who know the rumor is 100. So that means that is A. A is equal to 100. And it says here, the number of people who know the rumor doubles every day. So that means this is B equals 2. So we try to fill the table in, and it goes something like this one. So the initial is 100, and then it doubles every day. Therefore, we have the next day after, we have 200 already, and we have 400, 800, and 1600. Now, early on, we said that if the base is 2 and the value of A is equal to 100, we could now say that R of t is equal to 100 times 2 raised to the power of t, And we could simply solve for that unknown t through the Desmos graph. And you would see that the intersection of the graph of y is equal to 100. This is f of x actually. 2 raised to the power of t is the blue graph, and intersecting with this horizontal graph, which is the graph of y is equal to 350,000. Okay, so that's how we do this example. Now, we could also do this example by trying to make use of what we call the logarithm. So knowing that your RT or R of t is equal to 100 times 2 raised to the power of t, but your R of t is same as 350,000 in that case. So that means we could just simply equate your 350,000 to 100 times 2 to the power of t. Now, from here, we could simplify by dividing 100. Okay, divide this both sides of the equation by 100 so that we could have 350,000 simplified. So this is going to be 3,500. And this is 2 to the power of t, and we could just simply get their logarithms. The logarithm of 3,500 is equal to the logarithm of 2 times or 2 raised to the power of t. And that this is the log of 300, the log of 3,500 is equal to t times the logarithm of 2. And so your t would simply be equal to the logarithm of 3,500 divided by the logarithm of 2. We could divide both sides of the equation by the log of 2, so that you have your t will be equal to the logarithm of 3,500 divided by the logarithm of 2. So using our calculator, we could plug in the logarithm of 3,500, okay, and divide it by the logarithm of 2. And what do we get? We have 11.77. And this is actually the same value that we get when we use Desmos in this case. Moving on to this next example, we try to go over and characterize the functions. When I say characterize, we'll try to give the properties, the different properties, by stating the domain and the range, the intercepts, and the behaviors of the function. So first of all, so we could try to plot the points that we need in order for us to be able to graph this function in this case. So maybe we could the first point that we need is this point 0, 1. Take note that this is a very prominent point in the graph of any given exponential function whenever the value of a is equal to 1. Your b here is given as 2/3, and you see that this is actually between 0 and 1 because it's a fraction. Okay, it's a decimal value. Then also consider the point, this is the first point, the point 0, 1 that we need. Also consider that if x is equal to 1, then that means to say we have your y, which is actually your b, while your -1 will take the value 3/2. So what do you notice? These are reciprocals of one another. And take note that this is simply your 1b, and this is your -1 in the reciprocal 1/b in that case. We try to plot these points now. We could see them here and here. So this is your 1 and 2/3, and this is our -1, and this is our 3/2. Now we try to go over our first properties in that case. So by the way, this would be your graph in the domain of, so by the way, this would be how the graph looks like. And the domain of this graph is actually the set of real numbers, and the range would only be the positive values of the real numbers in this case, because the graph does not touch your x-axis and there is no point below it actually. Now the graph is decreasing, as I have said, while that is because your b is between, that is because your b is between 0 and 1. It is a fraction. The graph is continuous because it makes use of the set of real numbers for the domain. Okay, another property that is also considerable is the intercepts. So for the x-intercept, it does not exist here, okay? But the y-intercept, of course, is the most significant point here, which is your 0, 1. The behavior of the graph is this. The graph increases without bound as x approaches -infinity. So you see that our graph goes up as your x approaches -infinity. You would see here that your y goes up. So it says here that the graph increases without bound because our domain is a set of real numbers for x. Therefore, so as y. And the graph approaches 0 from above. Okay, the graph approaches 0 from above, it says here. Right, as x approaches positive infinity. And in that case, you would see that if we approach the positive infinity, you see, as x increases, that means it becomes positive. Okay? You would also see that the graph would approach the -infinity up to this point only. So it doesn't actually go down beyond your x-axis. So it approaches 0. Because later on you would know that your 0 is what we call your asymptote. Okay? So that means to say the graph approaches 0 from above. From above means it comes from the positive infinity going down and approaching your 0. The last property is, of course, the graph passes through these 2 points. Your 1b and your -1, 1/b. Okay? So, another problem here would be the projection of population in this case. No? First of all, you see here we have a very peculiar problem that talks about a population of, that's a c of t, no? The function c of t, of a place which is called Sokovia. The function is given by the formula C of t is equal to the equation. C of t is equal to 100 e raised to the power of 0.05t. And t here is the number of years after 2010. So 2010 would be the initial in this case, right? Now, we give an estimate in the nearest digit. So when we say in the nearest digit, because we're talking about population here, we will be rounding down our final answer when we talk about population. Of course, there must be no excess. Alright, let's try to give an estimate of the population in 2030. So to find the estimate in the nearest digit of the population, we first determine the number of years after 2010. So how many years have passed after 2010 when it already reaches 2030? That means it is equal to 20. So I hope that is clear. 20 years have passed. Right. Next is, we input that 20 to our equation. So in that case, you could be able to find out what the value of your C of 20 is. So what is C of 20? C of 20 is equal to 100 times the quantity A raised to the 0.05 times 20, and then that gives us our 21. We could easily input that in our calculator. So in this case, okay, C of t would be equal to 100 times the quantity. So your E here could be done by simply looking into our E. Here we have alpha, the scientific notation here. But we could also make use of this. Shift the natural log key. So it gives us already the placeholder for our exponent. And our exponent here is the product of 0.05 multiplied by, of course, the number of years, 20, and it gives us 271.82. But we just scrap the 0.8281 there, no? So we just have to eliminate the decimal and copy our whole number. That's how we do it. We don't round it up. Okay. We're asked to determine the value of t, then the years when the population would already reach 400. And how do we do that? As we go over looking for that value of t, you would be surprised to know that it's a very small value. Now, how do we do that? Of course, we make use of our Desmos, maybe. Equal to the equation 400 is equal to 100 times e raised to 0.05 times t. This could be done by the application of logarithms. No? Your C of t is given here as 400. Then we could simply equate this 400 to our given function. So our function is, this is 1 raised to the 0.05 t. And so, we could simply divide this first before taking their logarithms by 100. So again, you will be able to see here that we just have your e is raised to the 0.05t left on the right hand side of our equation, while in this case we just have simply equal to 4. Now we could take the natural logarithm ln because of this e. So ln of e raised to the 0.05t. But take note, your ln of e later on, which is going to be multiplied by your 0.05t, would be equal to 1. So what happens is that this is just simply equal to 0.05t, and this is still remaining ln of 4, so that your t will simply be equal to ln of 4 divided by 0.05. Again, using your calculator, we try to plug this in. Then we have, this time we use the ln here, the ln of 4. Then we divide that by 0.05. We get 27 point, so is that 27.726? Okay, 0.726 in 3 decimal places. And that is the same thing that we have obtained by making use of our graph in this case. And it says there that the graph tells us the point of intersection of the horizontal line. This is actually the horizontal line. Y is equal to 400, or C of t is equal to 100. And of course, this is your 27 point somewhere here, the value of x here, 27.726. So that we say that the number of years when the population will become 400 in that Sokovia is after 27.726 years in that case. Alright, now we have here a problem about a carbon-14 present in a substance. So again, we have C of t is equal to 20 times e raised to the negative 0.001216 t in that case. But first of all, we try first to answer the following questions. Is what is the initial amount of our carbon in that case? The initial amount would be, of course, your 20 in that case, because this is your A. Okay. Now, is the function growing or decaying? Definitely, since this is negative, therefore this is decaying. Okay, this is decreasing, it's decaying actually. How do we answer letter C? How much is left after 10,400 years? So we just simply go over and look for C of 10,400. And we say that after 10,400 years, our number of carbon-14 present would just be simply equal to 20 times E here raised to the negative 0.0001216, that is being multiplied by 10,400. Okay, and so we could use our calculator again to find out what your C of 10,400 is. So plug in your 20, then multiplied by your E. Your E here is ln, shift ln. Then our negative value, that is 0.30. We have 1216, and then after that we multiply this by 10,400. So 10,400, and then close our parenthesis here. No, not that. Move our cursor first, and that is equal to 5.6468. So what does it mean? It means to say that, alright, again, that is how many? 6468. It means to say that the amount of carbon-14 present in that particular substance after 10,400 years is just 5.6468 grams in that case. Right? Now, here are our answers. The initial amount is 20. The function is decaying. And after 10,400 years, the amount left is approximately 5.6468 grams. However, how did we arrive at 5,700 years in this case? Take note that we use graphing calculator to determine the number of carbon-14 present when the number will just be simply half of its original amount. So we use our graphing calculator to determine the number of carbon-14 present. So we use our graphing calculator, of course the Desmos, the number of years when the number of carbon present will just be simply half of its original amount. Means that your 20 will just become 1/2. And that is still 20 raised to the e times 0.000, that is 1216, raised to the power of t in that case. Now, what do? Simplify this one. This is 10 and this is 20, but again, we could divide this by 20. 0.0012160. and that is actually divided by 20. And so what remains on the left hand side would be just simply 1/2, or that may be 0.5 in that case. And this is equal to e raised to the negative 0.0001216t. Again, taking the logarithm of both, the logarithm, we don't use logarithm. ln of 1/2 is equal to ln of e to the power of 0.0001216t. But take note again that your ln of e is 1. Therefore, you just simply have this as negative 0.0001216t, and this is the ln of 1/2. And so we divide this by, okay, maybe just make use of this as so divided by 1216, negative 0.00011216. So this must be 0. And so we can now cancel this one, and our t will be equal to what? Make use of our calculator here. Our t is equal to, right, so we have here the logarithm of 1/2, ln, the natural logarithm of 1/2, ln of 1/2, or that is simply 0.5, and we divide that by negative 0.123. There are 3 zeros, 0.0001216. What do we get? We get 5,700. And in our graph, you would be able to see that there's actually 5,700 years. Okay, approximately 5,700 years in that case. So we are now up to our 7th example. Suppose that your 2,500 or 2,500,000 regular time deposit in your savings bank will grow 1% yearly interest. So excuse me. So how much would your money be after 7 years? So how long will it take for your money to grow to 3 million? So there are two questions here, no? So the first question would be answerable by this one. The solution is, from the given problem, the initial amount is given as 2,500,000. The rate is just 1%, or 0.01. Okay? To solve that, we will be using, of course, our discrete exponential function, d of t. d of t is equal to p sub 0 times 1 plus rt. So this is our growth factor in that case. Okay? So from there, we plug in our given initial amount, which is 2,500,000, 2.5 million. Then we multiply that by our growth factor 1 plus 0.01, and our time here is 7. In that case, number of years is 7. And you'll get 2,680,338. So you may do that using your calculators. To solve the time it would take for the money to grow to 3 million, then we use the same formula. And we just simply input your 3 million to our d of t, change the d of t, and we look for t. Again, in that case, using our graphical calculator or our Desmos, we will be able to see that our graph here is the point of intersection of our horizontal line. The horizontal line here is the 3 million, the line for 3 million, and this is a parcel of our graph, just a part of the exponential function, by which the intersection is 18.323. So that means to say, it will take 18.323 years before the money would grow to 3 million pesos. So that's how long it would take for the money to become 3 million. Alright, so the 8th problem. So the inflation rate tells the percentage by which prices increase. Okay? In our country, the Philippines inflation is recorded to be 6.4% this August of 2018. It's actually the fastest since March of 2009, but it's 9 years after. Suppose an individual retired and had a retirement of 1.5 million pesos. Retirement pay of 1.5 million pesos. Assuming that the inflation remains constant at 6.4%, determine how long it will take in years for that retirement pay to deflate to half of its current value. Note to say that the retirement income has deflated to half of its current value. That means that the prices have doubled in that case. Alright, with that we say our function would have been this, considering that p sub 0 be the amount, okay, of 750,000 pesos. Okay? Assuming that the inflation rate remains constant at 6.4, we can determine when the product will double its current value through solving the equation. So we are now going to look for the time, okay, the t in this case. Now, again, from there, we use the graphing calculator and we look for that as 11.7 years as shown in this graph. So I know that you could be able to use it, do it also yourselves in that case. Right, we still have another one. We have actually 10 examples to do. So the table shows the balance in the dollar saving account that grows over time since the initial investment. So this is actually $3,500 in the initial amount. Now create a model that describes the growth of investment and determine how much saving you would have after 12 months. So just to say, in this case, what do we do? So the first thing is, of course, we know that our growth factor would be 1 plus r. So our growth factor here would simply be the ratio between any of these values divided by its preceding term. So in this case, so the growth factor would be 3,542. Okay, we divide this by 3,500. So what do we get? If you try to calculate that, we have 3,542 divided by 3,500. So we have approximately equal to 1.012. And that's how actually we got this 1.012. Now we try another of our 3,585.5 divided by 3,542. Then, so that's approximately 1.0122. Again, that's the same. And so that's how we get it. Therefore, the saving balance in the account should be S of 12. And that is actually equal to 3,500. That's the initial times 1.012 raised to the 12 power. The 12 here is the time that we find out. Okay, so that's it. And for the last example that I'll be discussing, let's try to read this one. In 1971, Starbucks Coffee opened its first location in Pike Place Market. It Seattle's legendary open-air farmers market. Okay. By 1987, the number of Starbucks locations had grown to 17. And by 2005, there were already 10,241 locations. So, how do we do this one? The data below, okay, summarize lang dapat. The data below summarize the growth of this company from 1987 to 2005. By the way, this has been obtained from the Starbucks Coffee's website, starbucks.com. We try to determine the model that describes the growth of this number of Starbucks locations so that we could predict how many locations there would be in a specific number of years or after. So first we talk about modeling nearly exponential data. Functions are used to model patterns. Now there is the so-called regression analysis, which is defined as a process of performing mathematical computations to find the formula or model. So in this case, we're going to find for the model that would answer our question earlier. So a formula that best fits a set of given data for the purposes of number one, modeling, and of course prediction. That's what we're going to do a little later. Okay, now again we go back to our example. Let's try to determine the model that describes the growth of the number of Starbucks locations. The first thing we have to do here is to try looking into how we could plot the graph. So take note that to plot the graph here, it needs first the different data that are taken from there. Now, let us try to represent t as 0, and that represents the number of year in 1987. Take note that from our table, we have an increment of 2 years from 1987 to 1989, 1991 to 1993, and so on and so forth. Therefore, from the table that we are going to input in our graph, we have to start from 0 and to be followed by 2, 4, 6, 8, up to 18. Okay, after 18 years. And you see that these points represent the different ordered pairs. 0, 17 is here, 255 is here, and 18, 10,241 is this one. The next is we try to input a specific formula. Now, this formula would be y sub 1. Okay. This is the tilde. It's beside 1 to the left of your keyboard. That's the tilde. Now we have AB. A is our initial, and then your B is our base, and your X would be the number of years. And so we have here A is equal to 164.128, and B is 1.26072. Now later on, we try to plug this in so that we could be able to form that model in that case. So take note that A here has come up to be 164.128, and your B is 1.26072. It's just generated by the table which we have input in our graph. Now, our E exponential regression in this case, it is the model y is equal to A times E raised to the Rx. Then we will be able to get R here, and of course the initial value, which is the same, is 164.128 that we have obtained from our first equation rather. And then the second graph is this one, the same red. And so you say that your A and R are given, so we could have now our models. We make a table. And you may type in all the values of your x of 1. Take note there's an increment of 2 in that case. But it could easily be that instead of typing all the values, we could just simply make use of the Excel values. I have already typed in them, then copy. Then just simply paste them to our Desmos. Okay. And as you see, these are the points that represent the different ordered pairs in that case. We now type our function. We say y sub 1 is approximately AB raised to the x1, and that's it. Then I change the color to red in that case. And you'll be able to see the trend line there. And then another one is the E exponential function. This time I'll use E. A is going to be raised to E times A rather, raised to the Rx power, and this is the E regression exponential function. So I'll change this to purple to see the distinction between the two. So they almost have the same graphs as you see. However, they differ from the values of your B. I mean, later on I'll tell you why. And these models would now tell us that we could simply be able to find out that after 33 years in this case, for example, if you try to predict the numbers of Starbucks location for 2020, take note that this has been 33 years after its opening. And so we could use this exponential model for us to be able to find out the number of possible locations of Starbucks after 33 years. So for us to be able to predict the number of Starbucks location for 2020, that has been 33 years from 1987, we just simply input your 33 in this case, both for these models. For our exponential regression, y equals ab to the power of x, we have 343,239 locations. While for our e exponential regression, we have 343,217 locations. Take note, there may be differences for that matter. Now, what about the years 2013 and 2015? So maybe we could just simply make use of our calculators to find it out. In the year 2013, we have total locations of 67,805 using your first model. For the second model, we have 67,802. So a difference of 3. On the other hand, for the year 2015, for the first model, we have 107,771 and 107,767 for the second model, the e-exponential model. And so that's it. We are done with our 10 examples. I hope you have learned something for this example.